Let's cut right to the chase. You are literally bleeding marks in Cambridge Information Technology 9626, and it's probably because you're treating monitoring systems like simple on and off switches. Well, in this explainer, we're going to fix that instantly. All right, we've got a two-student duel right here. I want you to predict the winner right now. Student A claims sensors send data every few minutes or when the environment changes. But student B, they say sensors continually send continuous analog data that is converted via an ADC. Okay, if you pick student A, you just hit a massive grade boundary risk. Student B wins this every single time because top-tier marks absolutely require knowing that monitoring data flow is continuous. It literally never ends. Mastering this distinction, that's your ultimate payoff today.
So here's our quick roadmap. First, the sensor exam trap. Then, core sensors and ADCs, real-world scenarios, calibration, and finally, building top band answers. Let's get into it.
Section 1. The sensor exam trap. Intermittent versus continuous data.
Okay, so here's the non-negotiable reality of the situation. A microprocessor can only read digital data. When an analog sensor is sitting out in an environment, maybe it's reading the temperature of a river or atmospheric pressure, that data is continuous. It's analog. That means the analog to digital converter, or ADC, is the absolute bridge in any monitoring system. I mean, if you don't mention the ADC in your exam answer, your monitoring system literally cannot communicate with the computer. It's a total dead end.
Moving on to Section 2, core sensors and ADCs building the system.
You've got to memorize this step-by-step flow. It is the absolute skeleton of a perfect exam answer. First up, step 1. The analog sensor collects continuous data. Then, step 2, the ADC translates it. For step 3, the digital microprocessor processes and records it, usually comparing it to preset values. And finally, step 4, the system creates an output, like, say, triggering an alarm if a nuclear reactor is overheating. You know, pretty important stuff.
Now, examiners fully expect you to perfectly pair physical variables with their real-world applications. You can't just vaguely write, a light sensor checks water. No way. You've got to specify that a light sensor measures turbidity, which is the cloudiness of a river caused by pollution, or that a pH sensor measures the exact acidity of soil. Being precise like this proves you actually understand the technology. Now, in a moment, I'll show you the exact examiner clue about calibration that changes your answer completely. But first, you need the framework that makes that clue super obvious.
Section 3. Real-world monitoring scenarios, weather and ICUs.
Check out how a traditional mechanical tipping bucket is modernized here. So, instead of a human standing out in the rain counting marks on a graph plotter, a reed switch is used. Every single time the bucket gets heavy enough with rain and tips over, it activates the switch. That sends a digital pulse straight to the microprocessor to automatically count the tips and calculate the rainfall. It's just a perfectly brilliant example of automating an old analog process for a modern monitoring system.
Let's shift gears to a hospital intensive care unit, or ICU. You've got wearable sensors tracking vital signs like blood pressure and pulse. But listen closely, because here is a major exam trap. An ICU monitoring system is not a control system. It constantly compares patient data to preset normal values and simply triggers an alarm if data falls outside that safe range. It does not administer medicine. It strictly requires human intervention, like a nurse absolutely must step in. Whatever you do not call this a control system on your exam.
Section 4. Mastering sensor calibration, maintaining accuracy.
You know, examiners absolutely love testing you on why a system's accuracy degrades over time and how calibration restores it. Think about it. If your temperature sensor is measuring boiling water, but the output reads 95 degrees, your system is failing. Calibration compares the sensor's reading to a known, highly accurate standardized measurement, adjusting the algorithm so it reads a perfect 100 degrees again. It's essentially a reality check for your sensors.
Okay, let's actually test your understanding right now. Pause the explainer and predict the answer to this interactive challenge. Which calibration method is best for a sensor measuring a constant, unchanging temperature? Just think about how many measurement points you would actually need for a totally static environment. Got your guess?
Well, if you guessed 1-point calibration, you hit the nail on the head. Since the temperature never changes, you only need to take one single reading, compare it to a known value, and subtract the difference. That just becomes a simple mathematical offset added to every future reading to keep it perfectly accurate. Easy, right?
But what if the environment isn't static? This is where the complexity scales up. Figure 3.1 shows a 2-point calibration graph for pH values, which handles linear slope errors. You need a neutral pH plus either an acidic or alkaline solution to establish that straight line relationship. Then over in Figure 3.2, you have multi-point calibration. This handles complex, nonlinear curves, kind of like a hot liquid cooling down over time, where a simple one-point offset just isn't going to cut it.
Section 5. Building top band answers, the framework.
If you want to score in the top band, you can't just list facts and hope for the best. You need solid structure. Enter the Peel-J framework. Point, evidence, explanation, link, and judgment. The absolute secret to securing that A-star is mapping your IT knowledge directly onto this exact framework, especially when you run into high-level command words like describe or evaluate.
So let's compare two answers. The flawed answer says, ICUs use sensors to check on patients so nurses don't have to. Ouch. That scores 0 for technical merit. But notice how the top band answer leverages specific command word awareness? It starts with the point. ICUs utilize continuous analog sensor data. Then the evidence, converted via ADC. The explanation, comparing vital signs to preset values. And finally, the link back to reality, which triggers alarms for necessary nurse intervention. That right there is how you demonstrate complete mastery to an examiner.
So the winner of our two-student duel is pretty clear. You've unlocked the high-mark strategy for monitoring technologies, but to completely secure your grade, you must subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. And immediately click the next explainer. Because honestly, before you do, ask yourself, if an examiner asked you right now to explain the difference between monitoring and control in an ICU, would you actually pass or would you trigger an alarm? Click that next explainer to uncover the hidden traps examiners report every single year.